Okay, so the second example we're going to have for the energy conservation equation is going to be about a bar that's connected to a spring from one side, as you can see in this figure, and is going to be released from the position of the theta is equal to 0 degree until it's going to reach the theta of 90 degree. So basically, we're talking about this original position, and this will be the final position. We need to know what will be the value of the omega at the second position. So mainly in this example, we can see that the energy we're going to have is going to be, or the work is going to be done, is going to be first due to the weight. That's going to be changed the level from position 0 to position -1, for example. And we're going to have also another work or another potential, what we call it the elastic potential energy of the spring, which is going to be equal to the half multiplied by the K of the spring multiplied by the delta S. Okay, so this will be the main equation we're going to use. Actually, I added in the description of this video another video done by one of the universities which explain this topic. I know that we already have it done by the subject coordinator available on the canvas. That's going to be much faster if you're going to click the link below. So now we're going to start knowing that the initial upstretched length of the spring is 1 meter. That means that the length of the spring in this position is going to be 1 meter because 2 now minus 1, so it's going to make it 1 meter stretch. The other length here, or stretch length here, is what I'm going to sketch here. And sorry for that, the mouse doesn't work. Yep. So we can find the length of the spring at this position, which is going to be, that this is 4 meter and this is 2 meter. So that length is going to be under square root of the 2 square minus, plus 4 square. And we can find the length. But the stretching length of the S value is going to be equal to that value minus 1 meter, which is the unstretched length of the spring. Anyway, we're going to go through these slides. So first, we're going to define that the AB undergoes rotation about fixed axis through the A. And the state one is this one. We're going to have, again, the spring acting to the right, and we're going to have direction AM, AX and AY at the point A. The weight is going downward, and the second position, that will be the new length of the spring, and the weight is going to be at that height. Difference between the datum and this height is going to be 1 meter. Okay, and the mass is 10 kilograms. The S1 is 1 meter. The K is equal to 10 Newton per meters. And theta 1 is 0, theta 2 is 90 degree. The S2 is 3.472 meters. And the omega 1 is known as 0. The omega 2 and the VG2 are going to be required. Now, the omega at G is the velocity at G is going to be equal to the omega multiplied by the distance AG, which is 1 meter. Okay, so I just wanted to remember that. So we said that only the gravity force and the elastic force do the work. Conservation of the energy equation is going to be T1 plus the V1 equal to T2 plus the V2. And for the IG of the bar is 1 over 12 ml square. And it's going to be equal to 10 over 3 kilogram meter square. Now we come to the equation of the T first. So we said that we know first we're going to have the kinetic energy, which is going to be half of the mass Vg square. And we're going to have the other side is going to be the half of the Ig omega square. So we can find this equation given to us. We're going to substitute that the VA is equal to the RGA multiplied by the omega. Okay, and we can substitute that in this equation. Sorry, the VG, that's VG. I have many errors need to be changed here. And here, of course, we should have square. Okay, so we can substitute the velocity in that equation to be this one, omega r. Now we have everything is ready for us. We just need to substitute the value for the omega for the T1 to be equal to 0, and the omega 2 is unknown. So we can bring the equation to here. We're going to find the T1, which is going to be equal to 0 because the omega 1 is equal to 0. And in the case of the T2, we're going to use the Rg equal to 1, and the omega is omega 2. And we are going to substitute everything in this equation, and we'll find that the T2 is equal to 6.667 omega 2 square. Now we need to find the value for the V1 and the V2. So we said that both the spring and the elastic spring and the weight are going to do the work. So the V1 is going to be the work one for the elastic work plus the V due to the weight, okay, for the first case. So in the first case, the elastic energy is going to be half multiplied by the spring constant K multiplied by the stretching of the spring, which is the length is 2 meter. The S1 was 2 meter. And the initial length of the spring upstretch is 1 meter. So we're going to have 1 meter. So the Y1 was 0. So if I going to apply this parameter in the reverse equation, the K was 10. The stretch distance is the S1 minus the SO is 2 minus 1, which is 1. And I will find that the first half is going to be 5 plus the 10 multiplied by 9.81 multiplied by the Y1. The Y1 is 0, so I'm going to have the second part is going to be equal to 0. So the answer obviously is going to be 5 joule. Now we come to the other side. Now here the length is going to be different. Is something like 2 squared plus 4 squared on the square root minus 1 and then squared multiplied by 10 divided by 2. This will be for the elastic energy, and for the weight energy or the gravitational energy is going to be the weight multiplied by the Y2. The Y2 is 1 meter beneath the datum, and this will make it minus 1. And if I get to put all the parameters in the equation, I will find that the value for the work here is going to be equal to minus 37.83 joule. Double check that. Okay, now we have everything. We know that the V1 is 5, the T1 is 0, the V2 is minus 37.83, and the T2 was 6.66, I think. I don't remember. Omega 2 squared. So we're going to put that in the equation, 6.667 omega squared, I think. Anyway, we put that in the equation here. You can see that only the omega 2 is going to be unknown. I can rearrange the equation. The minus 37 will go to the left, and then we're going to have a positive 37.83 plus 5, and this will make it 42.83 divided by 6.667, and this will give me the omega 2 square, and the square root, I will find that the omega 2 is equal to 2.53 radian per second. Okay, so it's a straightforward answer. We just need to think about how we're going to calculate the stretching of the spring in the second case.